that there's tremendous potential in organisms to differentiate according to their environment and things like that. And that's part of microevolution, which we see happening, and I don't question it at all. Another thing is natural selection. And some people say, well, I don't believe in natural selection, but I'll tell you, natural selection is a fact, because if there's a herd of antelope or elk or gazelles, you know, that are running through the wilds, wherever they are, and there's a cougar or a lion or a tiger, and one of those animals is lame or has a defect in its hoof or something, or is blind, that's the animal that has a defect that will be eliminated. And basically, that's what survival of the fittest is. It's really, another way of putting it is the elimination of the unfit. It's the same thing as survival of the fittest. Now, it doesn't explain how they got fit. It just says that if you are not the fittest in your group, and you know, things start weeding things down, you're going to be the one that goes. And that happens, and nobody questions that. And another thing, I did work for about 10 years studying genetic mutation, or identifying genetic mutations in babies to help so they could be treated. And we do know these things happen, and that is changes in our DNA can cause diseases, they can cause all kinds of problems, and these things can happen randomly. It can happen from radiation exposure, it can happen from toxic chemicals, and some of them just happen spontaneously because we're exposed to things in the air and atmosphere and stuff all the time. In fact, UV light, skin cancer here in Arizona and Southern California, that's a big thing. Those are genetic mutations that are caused by radiation or chemicals, things like that. And we know those things happen. And so that's not a questionable thing, that that's part of microevolution. It's something we know that happens. But the problem is, evolutionists say, oh, these are all facts. Therefore, you have to believe our whole big story of what's called macroevolution. And they like to not use sometimes the word micro and macro. They want to lump them all together, but they're really two very separate things. Because macroevolution is supposedly what's happened over millions and even billions of years, times when no one was around to see it, and that, you know, we have to basically extrapolate and cannot test and cannot reproduce any of these things. And in fact, this one evolutionist, Eric Chasen, who was a late professor at Harvard, wrote, it's even more humbling at first, but then wonderfully enlightening to recognize that evolutionary changes operating over almost incomprehensible space and time have given birth to everything around us. Scientists are now beginning to decipher how all known objects, from atoms to galaxies, cells to brains, people to society, are interrelated. And he goes on, he says, we can trace a chain of knowledge linking from the evolution of primal energy, the Big Bang, into elementary particles and atoms, the evolution of those atoms into molecules, into galaxies and stars, the evolution of stars into heavy elements, the evolution of those elements into the molecular building blocks of life, the evolution of these molecules into life, and then the evolution of life into intelligence, and then even culture and technology. So all these things are just natural evolutionary processes going from small things to creation of atoms and all this stuff. It's just purely natural. Science can explain it all. And another professor, who's also deceased now, but from Cornell, this is really the behind-the-scenes mindset. This isn't a scientific thing, but this is the conclusion that most evolutionists have. And that is, he said, let me summarize my views on what modern evolutionary biology tells us loud and clear. There are no gods, no purposes, no goal of any kind. There's no life after death. There's no ultimate foundation for ethics, no ultimate meaning for life, and no free will for humans. Well, isn't that refreshing? So that's basically, that's the conclusion. If we are just particles, and that's all it is, then that's really, this is the conclusion you can draw from that. So, and finally, Richard Dawkins sort of summarizes the whole thing. He says, Darwin made it possible to be an intellectually fulfilled atheist. Because until there was evolution in some way of explaining how everything got here, that was a hard thing to be an atheist, because there was no explanation for the world, the stars, and everything. But now they can say, oh, it all just happened through evolution. But there's not just science and intellect that drives people to atheism. As you can see, Richard Dawkins has this bus tour that he did a while back, and a huge sign on it that said, there's probably no God. Now stop worrying and enjoy your life. Meaning, you can be immoral, you can do whatever you want, there's no consequences, there's no judgment. So there's clearly moral reasons why people might want to throw off the idea of God, because, hey, that gives you a lot more freedom to have fun and not worry about any consequences or anything. And this is a blank slide by design. That all these things, when I was younger, I was raised going to a church, but I wasn't really a strong believer or anything like that. But actually, I don't know, is there feedback? Is it possible you can turn this, or are there speakers on, if we can turn it down a little? Can you hear me all fine? Okay. But when I was younger, I really got into evolution, and I began studying and reading all the books and the philosophies, these things that I just shared with you here, and I became convinced evolution was true. And as a result of that, I became an agnostic at first, and, not knowing if there was a God, but eventually I was convinced there can't be God. Evolution explains it all. There's no need for God, and that's the way it was. So for a couple of years, I was basically an atheist because of evolution. But then, I won't get into it, I had a sudden conversion. I wasn't looking for God, He came upon me, and I had to start re-examining all the things in my life that I assumed were true, assumed were facts. And over the years since then, I ended up getting a PhD in biochemistry at Ohio State, and I've worked in various scientific fields and just done a lot of studying and reading. And these are what I like to summarize as what I call the 5 dirty little secrets of evolution, which I think are 5 of the key arguments that evolution claims to explain, but yet when you really start looking into detail, the facts overwhelmingly show that evolution cannot explain them at all. And the first one is the Big Bang does not explain the origin of time, space, matter, and energy. Because interestingly, if you start studying about the Big Bang, you realize, it starts with a cosmic egg. And the cosmic egg had all the matter and all the energy of the entire universe that we see. The Milky Way, all the galaxies, everything in this room was once in a microscopic thing smaller than an atom, this tiny cosmic egg. And then that exploded. So they're not explaining how the universe came from nothing. They're starting from something right at the very beginning. And so the big question that I would like to propose is, which came first, the cosmic egg or the cosmic chicken? Because, so that's the thing that I think I'm going to do some further research on. I'll skip over number 2 because that's tonight's topic. But this third dirty little secret of evolution, which I think I did here a couple years ago, is that evolution provides no scientific explanation for the origin of life. And this is one of those things that evolution talks about, how one form of life can have mutations and become a different organism. But the thing that evolution cannot explain is how that very first living cell came about, to begin the evolutionary process. And as it turns out, Darwin, and back in his days, and even 100 years ago, and even probably within the 50s and 60s, when I was young and DNA was just being discovered, cells were considered pretty simple. They were blobs of protoplasm. Little, under a microscope, they just looked like a little blob. There was not much detail. And as it turned out, they thought, well, this can't be that hard to form. They're just jiggling around, this can happen automatically. And people believe that dirty rags turn into mice and all these, spontaneous generation things too. Because it turns out even the very, very simple cell is so overwhelmingly more complex than anything we know. Evolutionists don't have a clue. There's no detailed story of any of the details of how non-living matter could become the first living cell. And I go through that in that talk. The fourth one is modern genetics does not back up the evolutionary tree of life or that the humans evolved from apes. And the tree of life is basically, you've probably seen pictures of this, is started with that first cell that they can't explain how the first living thing came about. But once it came about, then it became bacteria and fungi and plants, and it gradually got more complex, and there were jellyfish, and then there were invertebrates, and then there were reptiles and fish and birds, and finally mammals, and so it all branched out from this tree. Well, when you start looking at the details of the genetics, it doesn't back that up at all. You see things that are totally different that aren't related, they can't be explained. And then also you've probably heard how humans and chimps are 99% identical. That's far from the truth. And it's probably more, maybe 90% identical, but the amount of DNA differences in that 10% is hundreds of millions of detailed changes. There's no way that those changes could have happened in a few million years that supposedly it took for apes to evolve, chimps to evolve into humans. And there's many other things that show dramatic differences between humans and chimps, far beyond what evolutionists are willing to talk about publicly. And the last topic is one of my newer favorite ones, and I may have done this one here too, I'm not sure, but how evolution and science in general cannot explain human consciousness. And when you stop and think, what's the most important thing about your life? If you lost your arm, you would still be you. If you lost a leg, you'd still be you. If you're bedridden and can't move, you're still you because of your consciousness, your mind. And it's like, it's interesting, if we're just particles, you know, atoms and things like that that are connected together, how come we are able to think? We have this phenomena that we know as consciousness, that we have feelings, emotions, feel pain, you know, pleasure, and all these other things. There's no explanation for why atoms should be able to feel that, to have these conscious sensations. And that is still a total mystery that's hugely argued in science today. And evolution can't explain the most important part of what it means to be a human being. Of course, the Bible has other explanations for that. But tonight I'd like to get into the second dirty little secret, which is evolution has no scientific explanation for the fine-tuning of the universe. Or another way of saying the fine-tuning of the laws of nature. And another way of referring to this that I've seen and I like is it's called the Goldilocks enigma. And I like, here's a picture from the original, one of the first editions of Goldilocks from 1918. And you all know the story that Goldilocks lay down on a great big bed to try, but the pillow was too high and it wasn't comfortable. Then she lay down on a middle-sized bed and it was too low and that wasn't comfortable either. Then she lay down on the little baby bear's bed and it was exactly right. That's the words of the original, it was exactly right. And so very comfortable, she lay there until she went fast asleep. So the question is, why is it exactly right in our universe for life? And so that's the question is, can evolution explain why the laws of physics, the laws of chemistry, the laws of nature that define how our universe works, why is it just right that we are able to have living organisms like ourselves? And here's a picture. I don't have to explain this, I think, well, maybe to our person in the back. But for any of us, most of us here, we all know what these radio tuners were like, and you always know what it was like when the weather was really bad and you had an AM station, and it was really hard to get it right on that station, and if you were driving, and sometimes you'd have to shift it to get, you know, things. Fine-tuning is kind of like that, except to a much, much, much greater degree, where there's an infinite number of choices, and you have to get it tuned to one very, very, very precise value to make things work. And so we need to explain not only galaxies, that's a galaxy, spiral galaxy at the top, and planets and stars, and mountains and grasses and trees and all that kind of stuff, but also living organisms, plants and animals and people. How do the laws of the universe fit into all of this stuff? And one of the things that's interesting, the late Stephen Hawking was considered, you know, by many one of the greatest brilliant physicists. Of course, he's a avowed evolutionist. But he did write this, which is amazing. It says, the laws of science, as we know them at present, contain many fundamental constants or fundamental numbers, like the size of the electric charge of the electron and the ratio of the mass of the proton to the electron. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. So here's an atheist who said there's no God, there's no purpose, there's nothing behind the universe, but he's admitting that these constants that describe the laws of the universe appear to be very finely adjusted, and if they weren't the exact values that they are, we would not be able to explain life and the whole universe around us. And some of the things when they talk about these values or things, it includes things like gravity, electricity and magnetism, and something called the strong and weak nuclear forces. And I'll talk briefly just about all these in a little bit. But gravity, we're familiar, it's what holds galaxies together, it holds stars together and planets, and it's what keeps us, you know, keeps you in your seat right now. It affects every bit of matter that's attracted toward other pieces of matter. And the interesting thing about it is it's just perfectly tuned to allow these massive things in outer space to work, as well as for us to function here on Earth. You know. And what's interesting is if gravity, I mean, it could have, why does it have the exact strength it has? It could be an infinite value. It could be 1,000,000 times stronger or 1,000,000 times weaker or 10 times stronger, 10 times weaker. Why is it the precise value that it is throughout the entire universe? And it turns out if it was just a little bit weaker or stronger, well, if it was a little bit stronger, you could have the entire universe in a black hole where gravity is so great, everything is so tightly attracted, it's into this massive black hole where everything is so tightly compressed that nothing actually can happen. It would sort of be like a big bang that never banged. Everything stayed this tiny microscopic cosmic cave with all the matter of the universe so tightly held together, nothing would ever happen. Or if gravity was weak, you would have an explosion or stuff like this, and every particle would just be so unattracted to everything else, it would just diffuse away as gas. And there's no reason to explain if gravity were weak, you just have a universe of gas floating away from each other forever and ever and ever. There would never be any stars, planets, and of course, obviously no living things. So gravity itself is a very critical thing that we take for granted because every day of our life has been perfect, and we don't stop to think, what if it were just a little bit different? Another thing is, I won't get into these too much, but the people who believe in the Big Bang say that the explosion of the Big Bang was so precisely tuned, it was to 1 part in 10 to the 60th. That basically means that if you took that cosmic egg that formed every galaxy and everything in the entire universe, billions of galaxies and all, if you had 1 grain of sand too much or too little in that cosmic egg, you wouldn't have gotten the explosion that created everything we have today. It's that precisely tuned. It's just unimaginably precise. And the other thing is, the fine-tuning of the universe requires that if there was a Big Bang, that all the energy that we have today in the entire universe had to be in that tiny cosmic egg, which is something so incredibly unlikely that there's something called the Penrose constant, which is a number that says it's so unlikely that everything was so compressed in that cosmic egg, and not even writing that number would be a 1 followed by 10 to the 120th zeros, which means if you wrote a 0 on every atom in the universe, you still couldn't write this number. That's how huge the unlikelihood of everything having all this energy at the beginning. So getting back, we discussed a little bit about the cosmic level of fine-tuning and how everything's precise, but let's take a look at things that are more down to earth and affect us in our day-to-day life. And stop and think a minute. We take this all for granted, but if you think about the physical properties of the materials around you, there's things, is it a solid, is it a liquid, is it a gas? We're used to air being a gas. Water is generally a liquid, but as we know here, it's a few days of the year we get snow and ice, and other times you get the humidity. Fortunately not as much as we used to live in Ohio, and so even the humidity here is nothing compared to what we have back there. But so all these things we just take for granted. Colors of things, why do objects have the particular colors they do? The textures, the hardness, the brittleness, the slipperiness, the density, all kinds of things, melting point, freezing points, the electrical conductivity, why do some things conduct electricity, others don't? Why are some magnetic, others not? Why do some things dissolve in water, other things don't? Well, it just is. It isn't just is, there's reasons why all these things are that way. And these other things are chemical properties of matter. And even in our day-to-day life, things are they basic or they acidic? Does it rust or burn? How much does it react with other things around it? And think about everyday things that have chemistry in there, like batteries, fuels, paints, foods, drugs, poisons. All those things involve chemical reactions of one thing with another. Even tasting and smelling, those are chemical reactions where things are chemicals are touching other, triggering other things that cause chemical reactions to occur. And every part of your life itself and everything that goes on in your cells of your body involves thousands and thousands and millions of chemical reactions going on continually in your body. So at the end of this, if you get a chance, I just wanted to bring up, as I was a kid, I was kind of a science nerd. This is called the Handbook of Chemistry and Physics, and this goes back, they've been publishing this for 100 years or so, and back in the 60s and 70s, before computers, this was how you found out scientific information. And every chemical laboratory had a copy of this, and most scientists had their own copies and stuff like that, where you could look up melting points, boiling points, all this kind of stuff. But this is really a tiny fraction of the information out there. But all these numbers are precise, and they don't change. The boiling point of water at the right temperature and pressure stays the same, and these are constants and values that are measured. So if you get a chance, take a look at it. By the way, I measured it. It's an 8.5-pound book, and I forget how many thousands of pages it is, but it's just amazing all the details of the world that we take for granted. But I'd like to talk a little bit about atoms. In particular, carbon will be one that comes up here. And you're all probably familiar with the model of an atom, that you've got a nucleus in the center that has protons and neutrons, which think about as little steel balls. The protons have a positive charge, the neutrons have no charge. And around it are these little tinier balls called electrons that are spinning around, or a cloud of them basically around the nucleus. And that makes an atom. And there's different kinds of ones: carbon, hydrogen, nitrogen, oxygen, things of that sort. And it turns out today, I won't get into this in detail, but those protons and neutrons are not those basic particles that we thought they once were. They're actually made up of things called quarks. There's up quarks, down quarks, charm and strange and top and bottom and things like that. So this is just the names that physicists came up with. But we'll kind of skip this, but there's not too many of these, but basically that's what makes up all the matter around us. But each one of these elementary particles have a precise mass and precise properties of charges and various other things about them that don't change. They're the same everywhere in the universe. And those, basically, let's get back, these are the ordinary, you've probably all seen the periodic chart of the elements, and carbon is up in that top row off to the right, or second row off to the right, and oxygen's there, and there's quite a few things, a lot of metals you're familiar with, like iron and copper and gold and silver. All those things are pure elements that are on this chart. And they have the properties they do because of these forces we've been talking about. And I mentioned the nuclear forces, and you think, well, I don't care about nuclear forces, but the nuclear forces are what make atoms exactly the way they are with the properties they have. And if the nuclear forces were a bit weaker so that protons and neutrons didn't attract each other to form a nucleus, that each of those particles just kind of floated around and never attracted each other, we would only have one element on our periodic chart, and that would be hydrogen, because it's just a single proton. And that would be, the entire universe would just be hydrogen, just gas. It couldn't form anything more complicated than a single molecule of hydrogen. And so you'd have nothing of interest, not even stars, planets, rocks, nothing, just hydrogen gas everywhere. That's if the forces were weaker. And if the nuclear forces were stronger, you would just have all the protons and neutrons, there would be a single, most stable form of an atom, and iron happens to be one of the most stable ones we have today, but the nuclear forces aren't that strong that everything turns to iron. But it would be easy to conceive if those forces were stronger. We might have a periodic table that only had one or a couple atoms that were just super stable, and they never did anything else. And you couldn't have an interesting universe with just one or two elements like that. And I was getting into these, you can't really see all this stuff here, it's a little blurry, but there's just lots of huge numbers. Here, this is a little bit bigger, but there's all kinds of fundamental constants that even I don't know the majority of what these things do, but you're familiar, speed of light, you know, it's 299,000 kilometers per second, or 186,000 miles per second. Interesting about it takes a second and a half for light to get from the moon to us. It's not instantaneous, it takes some time. And there's various other things, the charges on various particles and all these things that determine how materials interact with one another in the world around us. And I'll get in a few of the others I mentioned, speed of light, the gravitational constant, things about the electric and magnetic constants which make all of our electronics work today. If it weren't for electrons having the properties they do and electromagnetic fields having the properties they do, we wouldn't have motors, we wouldn't have radios, we wouldn't have computers, lights, any of these things, if we didn't have all these things working exactly the way they do. And and other things, there's various other properties as well. And one of the things that's interesting is we're getting back to atoms. We have protons and neutrons and electrons, which form the atom at the bottom, and the electrons around. A proton and neutron, they're much bigger than an electron. And what's interesting, the proton and the electron have the exact same amount of charge, but exactly opposite. The proton has a positive charge, and the electron has the exactly same opposite charge that's negative. And so they balance each other out perfectly. But what's interesting, even though the proton and electron have the exact same charge, they don't weigh the same amount. A proton is much bigger. Anybody have an idea how much bigger a proton is than an electron? If you weigh them in a scale, how many times heavier a proton is?
A million?
A million? Okay, that's a little bit, yeah, not quite, but it's a lot. It turns out that the number is 1,836.152673. And this is a number, it just seems like, okay, this is an arbitrary number. But why 1836.152673? Why not 1834 or 1973? You know, that was a big year, or whatever. Or you know, 4,864 or a million. These are things that scientists have no explanation why it's this precise ratio. And what's amazing is it's not just a few atoms we measure. As far as we know from astronomy, from chemistry, from every experiment that's ever been done, this ratio is exactly the same throughout the entire universe. Every proton weighs the exact same amount as every other proton in the entire universe. Every electron is exactly the same as every electron in the entire universe. And even on the farthest galaxy, The proton is still 1836.1523, 152,673 times bigger than every electron, no matter where you get it from. Which is good news, because otherwise, if they vary throughout the universe, gee, if you went down to Phoenix, you might not be able to eat the food there because the electrons are too big or too small. So the nice thing is you can, the matter behaves totally the same everywhere in the universe. And this is an interesting thing, because remember at the beginning I quoted some of those evolutionists. Everything is evolving, everything is changing. That we have this change that this evolved into that, and this evolved into that, and this evolved into that. Even back in the 1870s, this was almost 150 years ago, James Clerk Maxwell, who was a devout Christian, by the way, he was probably one of the greatest physicists of all time, and he came up with a lot of the discoveries about electricity and magnetism that really made the modern world possible. With radio, electric machines, things that led into light bulbs and all that kind of stuff. Maxwell was one, there's things called the Maxwell Equations, which I don't understand, but I mean, he was a genius, but he was also a believer. And this was the time, in 1858 was Charles Darwin's, 1859 was the origin of the species. So during that 10, 20 years, that was when the beginning of the evolution debate started. And Maxwell wrote this back in 1873. And I'm going to read this, and this is amazing because it's still totally true today. It says, no theory of evolution can be formed to account for the similarity of molecules, for evolution necessarily implies continuous change, and the molecule is incapable of growth or decay, of generation or destruction. None of the processes of nature since the time when nature began have produced the slightest difference in the properties of any molecule. We are therefore unable to ascribe either the existence of the molecules or the identity of their properties to the operation of any of the causes which we call natural. On the other hand, the exact equality of each molecule to all others of the same kind gives it, as Sir John Herschel, another Christian well-known scientist, said, the essential character of a manufactured article. And I love this because evolution says everything's evolving, everything's changing. But the reality is no. And if you talk to somebody, well, do you believe everything's evolved? If somebody's an evolutionist and they say, well, do you believe everything's evolved? Absolutely not. And they say, well, do you believe it? Oh yeah, everything's evolved. Well, why is it that every electron, everywhere in the universe is exactly the same? Every proton is exactly the same. And James Clerk Maxwell gave a really stirring thing when he said, it gives the character of a manufactured object. Which then you ask, who's the manufacturer? And that's the kind of thing that evolutionists gloss over. Everything's evolving. No, the basic fabric of our universe, everything around us is made up of these indestructible particles that are unchanging and give the appearance of being manufactured objects. And like I say, I'll just get a little bit, you think about a lot of the inorganic, these are the non-living chemicals of life, things like nitrogen, oxygen, water, carbon dioxide, ammonia, iron oxide, which is rust, various other paint pigments, titanium oxides, hydrochloric acid, sulfuric acid. These are all formulas for common things that you see in your household or you've heard of before. And you notice they're all very few, just a couple, 2 oxygens and an oxygen, an HCl is a hydrogen and a chloride. The most complicated thing I think I have up here is sulfuric acid, which has 7 atoms connected together to form sulfuric acid. So most atoms don't connect to a lot of other atoms. They can only connect to a few. And you get, these basic compounds that we're familiar with in our everyday life. And actually, this is something, we live in Prescott Valley, and I guess I'm going to have to check out your granite belts because we have our own granite belts, which are like this, and we love to go biking through there. It's these massive, gorgeous rock formations that even when you look at rocks, granite, it's a mixture of all these oxides of silicon, aluminum, potassium, sodium. It's a mixture. So when you look at a granite rock, next time you're out hiking or doing anything, and it's just a rock. It's an amazing thing. It's a structure that's made of these same atoms that are found everywhere in the universe. They're exactly the same, but when they're mixed in this particular mechanism, they can make these amazing rock formations that have these structures and hardness and all the things that we otherwise take for granted. But what's really interesting are things called organic molecules, which are given the term organic, meaning they are found in living organisms. And one of the key things about organic compounds is they all contain carbon. There's a variety of ones. Like the top one is octane, which is in gasoline, but that's from the breakdown of plant materials, things like that. There's bottom one is glucose or sugar. The second one on the bottom right, that's a really important one called caffeine. There's the hemoglobin, the heme portion of protein is the one that has iron in the middle, but all these are made up of carbon atoms. Proteins and DNA are made up of carbon atoms. And there's a bunch of common organic compounds that do things like methane, natural gas is methane, which is carbon with 4 hydrogens hooked on it. And there's a whole variety of glucose, sucrose, but rubbers, plastics, oils, fats, drugs, vitamins, steroids, proteins, and DNA are all made up of complex compounds with multiple carbon atoms connected to one another. And carbon is a really amazing, out of all the atoms in the periodic table, there's only one other one that can even connect with 100 other atoms, and that can only be done in laboratories under very specific conditions. Silicon can form, I think, a couple hundred silicon atoms can be connected together, but it's very unstable, and it's not something you ever run into in nature. But for carbon, connecting to 10, 100, 1,000, million, it's almost unlimited how many atoms carbon can connect to itself and form long chains, rings, and all kinds of amazing complex structures, because that the properties that created atoms made the carbon atoms so that it can connect in these amazing ways, that it's not permanently connected, but they can be connected this way, that they're stable and can form these huge compounds. I worked for about 4 years. I went to Ohio State, where I met my beautiful wife in the back there. And this is Chemical Abstracts, is the building. It's hard to see at the bottom here. But it was right near the Ohio State campus. And what they did was they registered all the chemical literature that was produced anywhere in the world, in every language. And if anybody created a new compound, discovered a new compound, or anything like that, they registered it, they gave it its own unique number, and entered it into a computer system so anybody could search for that chemical and its properties and the number of atoms it had and all kinds of things about it. And so it was a huge, every chemist knows about chemical abstracts. And it's amazing. And they have 186 million unique chemical compounds that they have registered in their computer systems today. And more than 70 million protein and DNA sequences and billions of properties of all these millions of compounds. And that sounds like a massive number, 186 million different compounds that they have identified and have different forms. All that's from that periodic chart because of the properties we have. But nearly all of those compounds contain carbon. And including, in particular, DNA is something that we've heard about as our genetic material. It's these these are the 4 different bases of DNA. There's adenine, guanine, cytosine, and thymine, and they can connect to each other and form base pairs and carry genetic information, and it makes it easy to copy the information. But they can connect these little things, these individual bases can be connected almost infinitely from one to the next. And this is sort of a schematic or a diagram of some of the sequences that are found in in each of our living bodies. We have billions of these bases that you inherited half from your mother, half from your father. There's information, a code that tells how to make all the parts of your body, how your body can function, and everything like that. But what's amazing is this is what the actual genetic material looks like, the chromosomes. If you look under a microscope, you just see these little blobby things, and at first scientists had no idea what they were. And there's 23 pairs of things. You got 23 from your mother, 23 from your father, so you now have 23 pairs or 46 chromosomes total. But what's amazing is each one of these little microscopic things, every cell has it in your body, 10 trillion cells. Every cell has a complete set of all this DNA. How many carbon atoms does it take? And what's interesting is, if you take chromosome number 1, which is the largest chromosome, every cell of your body, and your fingers, your hair, your eyes, your liver, your kidneys, every cell has all the complete set of DNA, and every cell has a copy of chromosome number 1. It has over 8 billion atoms connected to one another into a single molecule. That's just an amazing thing. And like I said, other than carbon, no other atom can even connect to more than 100, and even that's extremely unstable. And yet in your body, you have these massive molecules that contain billions of atoms in a single molecule. And your body's able to make copies of that almost perfectly. I mean, to copy 8 billion atoms into another. These things, it's mind-boggling. And in every single cell, if you added up all the 46 chromosomes that I showed you previously, men have about 383 billion atoms in those 46 chromosomes. And women actually have more information because they have 2 X chromosomes. Men have the little Y chromosome, which doesn't have as much information. So women have another 14 billion bits of information in them. That's why they can think and do 2 things twice, because men are missing 14 billion atoms. But that's almost 400 billion atoms in every single cell of your body, times 10 trillion. That's how much information it takes to run a human being. And without this ability to form these massive, huge molecules, you wouldn't be able to have the information that it requires to have an organism as complex as human beings. They have all the functions we have, the motion, able to digest food. You know, you think of all the systems we have, breathing and respiration, digestion, reproduction. And like I say, we're factories that can make copies of human beings, which that alone is just mind-boggling. But that's because this massive amount of information, it's so tight, so compact, it fits into a cell so small you can't see it. Every cell of your body has this information. And another chemical I like to mention, very simple, we take for granted, is water. Now maybe we don't take it for granted as much here in Arizona as they do in other parts of the country, because we really like this. But there's a lot of interesting things about that. We've got a ton of it on Earth, and it's not common throughout most of the universe. 71% of the Earth's surface has water. And interestingly, if the Earth were flat, if there were no mountains and no ocean basins, and the Earth were like a cue ball, there would be enough water to cover the entire Earth to a depth of 2.25 miles. So it's interesting when people say, well, how could there ever have been a flood? If the Earth didn't have the mountains that it had before the flood and didn't have the ocean basins, even if it had some hills and stuff like that, there still would be on average 2 miles of water to cover the entire surface of the Earth. And it's interesting, in the Psalms it said after the flood the mountains rose up and the ocean sank down, which it describes even these ignorant peasants in the middle of these new plate tectonics and all these ocean things, the mountain building and stuff, before scientists had a clue of how that happened. So, but anyway, water is an incredible thing. It's called the universal solvent because it can dissolve so many things. It has a high heat capacity, meaning that if you add heat to it, it takes a while for it to heat up and it takes a while for it to cool off. So that helps us maintain our temperature of organisms, since we're mostly made out of water. And there's a lot of other things. The fact that it can be solid, liquid, and gas in the temperatures that we live in our world is dramatically important. It helps the water cycles and all the kind of things that happen. There's a huge number of properties, and I would like to mention, if you're at all interested in water, Michael Denton, he wrote a number of great books on intelligent design and things like that. But one of the ones he wrote is The Wonder of Water. And I mean, he has some theistic evolution beliefs that I don't agree with, but the properties of water are so numerous and so amazing. It's just, we take it for granted. And yet, if water didn't have all these properties, we would not be able to have life as we know it today. And so getting back to this tuning of all these things, we talked about gravity and electromagnetic forces and nuclear forces and 20 other different things. All of them, imagine not just having one dial, but you have a minimum of 20 to 30 dials of all independent things that have to be finely tuned to one precise value out of an infinite number of possible values. Why is 1836.152673 the ratio of a proton to an electron? Why not tweak it a little bit more, a little bit less? That would have totally changed all the chemistry of the periodic table and almost certainly made any kind of life like we know impossible. But every one of these dials has to be perfectly tuned at the same time, and they don't change. They stay the same through all history. They stay the same everywhere in the universe. How did that possibly happen? If you ask in evolution, if there's no God, there's no creator, why is everything so perfectly tuned to support the universe and life like we have? Even Stephen Hawking said it's amazing when it's fine-tuned. Well, their only answer is, well, there's no God, there's no intelligent designer, there's no creator, but there's the multiverse. And you think, well, what's that? And basically they say there's no need for an unseen creator or because we believe that there are an infinite number of universes out there, and we just live in one of them. And if you have an infinite number of everything, you're guaranteed to get every possible thing that there is. So that's basically, they say, we don't want to believe in one unseen God, but we will believe in an infinite number of other universes. Well, the interesting thing is, they say that, when I was young, the universe was everything there is. Well, now it isn't. The universe is just everything we can see, and the multiverse is other universes that we can't see or know anything about. And there's all kinds of bizarre types of theories, which tells you that they know nothing about it. There can be quilted, inflationary, brane, cyclic, landscape, quantum, holographic, simulated, ultimate. If all these different types of multiverses are all possible, that tells me that they don't know anything about any of them. And the reality is we have not observed any other universe other than the one we live in. So all of this stuff is pure speculation. And here's Paul Davies, who I believe is an evolutionist himself, that he wrote about something about the multiverse in New York Times, and he said, for a start, how is the existence of these other universes to be tested? To be sure, all cosmologists accept that there are some parts of our universe that are beyond the reach of our telescopes, but somewhere on the slippery slope between that and the idea that there's an infinite number of universes, credibility reaches a limit. And he talks about more and more has to be accepted by faith, and less is open to scientific verification. And these multiverse theories are therefore reminiscent of theology discussions. They invoke an infinity of unseen universes to explain the unusual factors of the one universe that we do see. And it's just as ad hoc or random as saying that there's a God behind it all. So the multiverse theory may be dressed up in scientific language, but in essence it requires the same leap of faith. So he's saying that people say, well, we don't need a God, we just have multiverses. This is totally faith in an unseen, infinite number of universes. And so it's like, well, we don't, I would rather believe in one God than in an infinite number of universes. And then another thing about this is, they say, well, if there's an infinite number of universes, anything that can happen will happen in one of them. Well, that's not always true, because you could have an infinite number of hydrogen gas universes where the laws of physics are so bad that there's nothing but hydrogen and nothing interesting ever happens, and there's an infinite number of possibilities of those. And the other thing is to say, well, if anything can happen, could there be a godlike creature evolved in one of those universes? And that would probably get, well, you said anything can happen. And it's like, well, yes or no. And so the thing is, they say, well, we don't want to believe in God, but we want to believe that everything else can happen except God. That's the only thing that can't happen in the multiverse. But the basic thing is, anybody who tries to explain why we have this fine-tuning of the universe, there's no reason why these values have the values they do. And yet they're constant, they don't change anywhere in the universe. And like I say, if anything else, just remember the 1836 portion. And actually, these are only the first 6 decimals. It trails off, and it goes on forever. We don't know how precise it is, but everywhere in the universe, every proton is 1836.152673 times bigger than every electron. And like I say, the phrase that James Clerk Maxwell quoted was, "This gives these atoms the essential quality of a manufactured object." And that's why evolution still has no scientific explanation why everything is exactly right. And with that, I will open for questions.
Do you mind